2014. It's the second Empire JS, which is great news for all of you who like things happening more than once.
Yeah, we're only doing even years, so if you're here in 2012, it was great. Have a good 2015. We'll see you in, I don't know.
We'll see you in 2000, I don't know, this decade. We are here at beautiful location 5, right near the construction site that will soon be the 7 train station, I think, which is exciting. What else do we? Oh, I'm Adam. This is Alex.
Hi.
We are your redheaded hosts. Fun facts about us: we have the same initials.
AJS, Alexander James Sexton.
Adam Jonathan Sontag. Also, our birthdays are 4 days apart. So if you have ever owned a liquor store in San Diego, you might find this impossible to comprehend if we ever walk in at the same time.
The old Steve the liquor store guy.
Steve the liquor store. Anyhow, we're really excited to be here, and we should get moving. But first, I wanted to give a shout out to Etsy, who sponsored that lovely breakfast. And woo! And also, who enjoyed the hand-cooked bacon? That was cooked by engineers. That's. There's Wi-Fi, which stands for wireless fidelity. That's how you get on the internet. The network is called Empire JS, and the password is JavaScript in lowercase letters. What does that even say?
Can't read his own handwriting.
It's just a set of loops.
There's a roller coaster outside. It's loops.
We do have a code of conduct, which is the JS code of conduct, and Charlie summarized it acronymically with that NYC stands for No Yutzes Central. So don't anything that someone would describe negatively in Yiddish, don't do.
If something does happen, please contact us or Charlie or someone you saw making breakfast that looked like an engineer. And we take that stuff very seriously, so even though that's a funny joke, we take it seriously.
And the last thing I figured out, it said hand-cooked bacon. So I hit that point already. Anyhow, we should probably start the conference, right?
No!
Woo! Our first speaker comes to us from over there.
The construction site.
Yeah, well, beyond the construction.
Jersey is what you're saying.
Yeah, we actually moved this here because we wanted to get some of that Jersey script mojo into the Big Apple. And few people know this, but Empire JS actually stands for, Alex.
Empire Jenn Schiffer.
Woo!
Welcome to the stage.
Does this work? It works. Okay. I make this really. Woo! Is that too loud? It feels like it's too loud. Cool. Just want to make sure. How's everyone doing? Good. Yay. So. Awesome. So good morning, everyone. I'm so excited to be here. I am going to be talking about sorting, which is really fun and exciting, right? My name is Jenn Schiffer. You can find me at Twitter at the same name. I'm going to come up here. I make pixel art, and I make tools for making pixel art at make8bitart.com. I am an engineer at Boku as of a few weeks ago. I'm so excited to be there. And as Alex and Adam both point out, I do live in New Jersey, in Montclair. I'm moving to Jersey City in a month and a half. You can cheer for New Jersey.
But if you
turn back time to the mid-'80s. I was born in Sunset Park and grew up in Bay Ridge, Brooklyn, here on top of Mike's Donuts at the corner of Bay Ridge Ave and 5th Ave. And down the block, my grandpa, Big Vinny, owns a bait and tackle shop still. And this is me back then with our really cool New York poster on the wall to remind people in New York that we're in New York. Back when I was a little Jen with the same hairstyle, I was really into solving puzzles and sorting things. My grandmother, Dottie, who raised me at that age, she used to take me to all of the McDonald's in Bay Ridge, and we wouldn't eat the food because I just wasn't into it. Also, we were going every day. But we would get all of the little Lego kits that they would have in the Happy Meals back then, because Happy Meals used to have really cool toys when we were younger. And I used to like to make cool things out of Legos and sort them, and really that sort of laid the foundation for me going on to college and studying computer science. But like, ew, college, like huge waste of time, right? Actually, no, college is awesome for me. I really loved it. One misconception that people have about college and web development, you have the people who are interviewing us that think that you need to have a degree in computer science to be a web developer. How many people here don't have a degree? Most of us probably don't. That's totally cool. How many people here have a bachelor's degree in computer science? How about a master's degree? Not too many people go that path. The misconception is that computer science and web development are the same thing, but it's actually not. Computer science as a science is generally more theoretical. I did a lot of research through grad school on latent semantic indexing, which involved a lot of sorting and matrix multiplication, and I don't use hardly any of that in my career of web development. But some of these theories can be useful, which is why I want to give this talk. A lot of people, if you've gone, how many people here have gone to school have seen this book before and have read it? the algorithm Bible, Intro to Algorithms. So all of the stuff in my talk today generally comes from this book, which I turn to quite often when I do my research outside of development. But since we all handle sorting in some sort of way in our program implementations, and also we all deal with algorithms, this will hopefully be useful to you. So in the Corman book, it defines an algorithm as any well-defined computational procedure that takes some value or set of values as input and produces some value or set of values as output. So who here has designed, written, or implemented something that takes an input and gives an output? Okay, you all should raise your hand. Even if I didn't become a computer scientist or web developer, that little Jen from the previous photo took Legos as an input and produced buildings and cars and stuff as an output with those little Legos. There was an algorithm that went into the design of taking these little pieces and coming up with something even greater. So even at the little kid level where we're dealing with art as opposed to science, there's still algorithms involved. So it's still important, I feel, to study this a little bit. This talk will hopefully give you a base if you've never gone into algorithms or never taken a course in algorithms, to sort of look at things differently when we're programming in JavaScript. So we're going to do a little bit of JavaScript. We're going to deal with some sorting algorithms, and I'm going to talk a little bit about efficiency and complexities. So I'm going to say things like big O notation, and hopefully you're not like, oh no, and leave the conference. That would be terrible. Who in here is a JavaScript developer? I know we're at RailsConf right now, but I'm hoping there's some JS devs here. Awesome. So the cool thing about computer science that you can't do in web development is you can make assumptions and create this theoretical world where you make up your own rules, and all of your experiments have to apply to them. So I can make the assumption that we are all JavaScript developers, and we only sort arrays of integers. That's insane in web development because you don't get to make those guarantees, but this is a computer science talk. We are only sorting arrays of integers ever. You're probably saying, understanding algorithms and their analysis is friggin' hard. I understand that. I mean, I've been studying this stuff for years, and I myself have to open up the Corman book in order to work on stuff for these slides and to better understand different algorithms that might help me do things like sorting and search and stuff like that. That's fine. Also, it's like 9 o'clock in the morning. 9 a.m. is hard for a lot of y'all. How many people here are not usually working at this time of day? I want to see everyone at Boku raising their hands. So we're going to add to the assumptions that it's like 9 a.m. So if you don't exactly get everything that I'm saying, that's totally okay. The slides will be up later, but I'm going to try to go through things a little bit slowly for both myself and y'all. So people who know me know that I like to tell jokes and write satire. So who wants to hear a joke? Sorting joke. Okay. When is 10 less than 7? In JavaScript. So how many people have seen tweets of people who are anti-JavaScript posting this, saying this is the reason why you shouldn't program in JavaScript? Yeah, which is completely asinine. So yeah, in this example, I don't know if it sounds good up here. So, oh, that's terrible. Give me a second to fix that. So if you call sort on an array of numbers, but you just call the JavaScript sort function, does that look better? Yay! CSS. So if you call the JavaScript array that prototypes the sort function on an array of integers, because as per our assumptions, we are only sorting integers, that weird 10 coming before 7 thing happens, which is kind of like, maybe makes you want to think, well, why would I deal with JavaScript if it doesn't even know that 10 comes before 7? So it's like, why? Well, because the sort function is lexicographical. It's a dictionary sort. If you think of these numbers in terms of not actually being integers, because the computer might not necessarily know that they are, the 1 in 10 is the first column of that sort of string, and 7 is the first column of that, and 1 comes before 7. That's what it thinks. And you might think like, oh, that's like ridiculous. Well, maybe we should rename sort to sort lexicographically, kind of like PHP likes to do with no naming conventions and stuff like that, which is fine, because JavaScript is just PHP without all the question marks. So this sort function is like an abstraction. There's stuff happening under the hood that we don't have to deal with as developers, which is great, but then you're like, well, what exactly is it doing, and what's going on that's wonky that's making that 10 less than 7? And really, it depends on the browser that you're dealing with. ECMAScript doesn't have a standard, and this is a quote from it, doesn't have a standard for what sorting algorithm a browser has to use. And even, and I'll go over what stability means, the sorting doesn't even have to be stable. It just sort of gives these requirements as to what returns should be. But we do know that sort has to be able to take a compare function, and that's what we end up using. So if we wanted to sort integers, we put in a sort function that takes in arguments A and B and returns the difference between them. And when you're returning the difference, then we know that we're dealing with numbers, and the difference will let us know if the item is less than the other one or not. And then we end up getting our correct array of 1, 7, 10, our sorted function there. How many people have used this method for sorting integers? All right. Okay. So just to go a little more in depth with how it works, and let me make sure that you can see it pretty well. So yeah, we have our input there. This is upside down. So we have our input 7, 10, 1. This is our function, and first it compares 7 to 10. Well, 7 minus 10 is a negative number. We know that then 7 is less than 10, and we don't really have to do anything. And then it compares 10 and 1. 10's greater than 1, we can flip them, and then 7 compared to 1, we can flip them, and then we have our output 1, 7, 10. It seems a little bit easy. It's really hard to sort of pull away from like what our eyes and what our brains are seeing in computing as opposed to what the computer is computing. And that will delve more into with stability. But if we wanted to sort in descending order, that's really easy. We can just send the opposite difference, b minus a, and then we have our array 10, 7, and 1. So this makes sorting integers really easy. With JavaScript, you just have to give it a little push in the right direction to know that it's not supposed to be a lexicographical search. How many of you thought that this was going to be a joke talk? Everyone at my job. Suckers. So there are 3 important characteristics of sorting. Stability, as I mentioned before, the ECMAScript standard says that sort doesn't need to be stable. Runtime analysis, which is that scary big O, big omega, big theta notation that causes large dropout rates at the computer science undergrad and graduate level. And then the algorithm's implementation itself. So stability is an interesting concept. A sort that's not stable is not necessarily a wrong sort, but it all depends on what type of data you have and what integrity you need to keep with it. So stable sorts maintain the relative order of items with equal values. So if we have this array of first names, Alex, Juan, Jen, and Adam, and I want to sort by just the first letter, well, you're looking at the array right now and you're probably thinking like, oh, I'm going to sort this in alphabetical order, so it will be Adam, Alex, Jen, and Juan. But that's not exactly the case. That's not a stable sort, because if you look at the original array, we're just sorting by first letter, and Alex comes before Adam, but they're equal values. This is the only time Alex will ever come before Adam, and Juan will ever come before me. So a stable sort will keep Alex before Adam when we're just sorting by that first letter. Again, directions are really important. You want to make sure that you're directing the computer to sort the way you want it to sort. So even though this is a correct order, Adam, Alex, Jen, and Juan, because the first letters are alphabetical, it's not a stable result because relatively Alex came before Adam, Juan came before Jen. So again, even though it's correct, which is why I think the standard doesn't require stability, if you need high integrity with your sort results, or maybe down the line you're looking for stability, that's just something to think about. And there are different algorithms, as we'll go over, that are stable and some that aren't stable. I think Firefox, at least, mostly uses merge sort for sorting integers with that sort function, and merge sort is a stable algorithm. Runtime analysis, that order of n and all that sort of fun stuff. How many people here have encountered O notation? How many people here have had a job interview for a web developer position and they've asked you about the order of a function, which is kind of bullshit. It's a terrible interview question. So it gives us a variable to compare algorithms where O of x is the number of operations it takes to get from point A to point B, and it's a function of n items in our array. Big O is the order for the worst case scenario. So sometimes you might have an array that's in reverse order that you have to get in ascending order. That might be a worst case scenario. It's completely unsorted and messed up. Big Omega is like the best case scenario, where maybe like you just have a couple of items that are out of place, but it'll go fairly quickly because it's nearly sorted. And big theta is like the average case scenario. But when doing analysis, big O, worst case scenario, are the things that we usually look at. And it's really not the be-all and end-all for determining what the best sorting algorithm you have is, because some algorithms that are super fast require a lot of space and temporary arrays for popping in things and recursion. And you might not be afforded that space, so you have to go for a slower algorithm that doesn't take up a lot of memory. So these are some things to think about. Some people say like, oh, well, don't ever use insertion sort because merge sort is faster, but merge sort takes up a lot of space and I might not have that, so you have to do insertion sort. And this is the reason why there are tons and tons of sorting algorithms available, because you have to think about what space you have, how much time you have, what kind of data that you have. Thanks. And so this is just one piece of the puzzle for picking what you want to do. So what's the deal with big O? So here we have this really cool table, sort of down there, that show the items, number of items n in our array. And then there are different types of algorithms that are constant, logarithmic, linear, quadratic, and cubic. Of course, if you have like a nested for loop in your algorithm, that's usually a quadratic order. And so when the number of items increases, of course, quadratically, so does the amount of operations it takes. And if you have like a sorting algorithm that is so slow that it's order of n cubed, you might not ever see that array come out sorted in your lifetime. So we're thinking, in my examples, of small arrays of like 3 to 5 numbers. But if you're a computer scientist doing research on big data, and I'm not just saying big data as like an SEO guru blog term, but actually like literally like an F-ton of data. You might need some like clusters and parallel computing, ooh, scary, in order to compute something of that nature. So we like to generally keep things in the logarithmic column, because look at how nice and fast those are. In order to do logarithmic sorting, we have to do recursion, passing the work off and breaking things off into smaller bits. Fun stuff. And here's just a complexity chart. This person made at bigocheatsheet.com a really cool interactive application with tons of charts and stuff like that that show big O complexity. And so with the x-axis being the number of operations, y-axis being the number of operations, x-axis being the number of items, you see things get really compute intensive really quickly. Unless you go for the logarithmic ones, n log n here. Have I ruined your conference yet? Are you all here with me? So there are 3 kinds of sorting algorithms I'm going to go over with you today. I'm going to go over insertion sort because it's a really good intro to a somewhat slow, somewhat fast, depending on how much data you have, sort. I'm going to go over bubble sort because it's got a fun name, and also I feel like anybody who hasn't taken an algorithms course has heard of bubble sort and knows that you shouldn't ever use it. But they might not know why, so we're going to go over that. And then merge sort because it's a fast sort and it's what most browsers use for that array.prototype .sort function in JavaScript. And for each algorithm, I'm going to go over the pseudocode, an overly simple example using like maybe 3 items in an array, and then the implementation in JavaScript. And you might think, well, why would I ever want to implement a sorting algorithm in JavaScript when I could use .sort? And again, as I break everything, depending on what type of data you have, you'll see that maybe you don't have the space to do merge sort, and you want to use that space for something else in your application. Well, you're going to know how to do insertion and bubble sort, and you can implement that. And you'll see how easy sorting algorithms are to implement. And I feel like those are better interview questions if you're hiring web developers than asking what the order of, selection sort is. So back to our assumptions. The pseudocode that I use uses a 0-base index, and this might seem like no shit because we're computer science people, web developers, of course it starts at 0. But a lot of stuff that you find online and in textbooks, pseudocode might have been written by mathematicians, and mathematicians that I've worked with in grad school, they always go with a 1-based index. So when you're looking at resources online, you want to make sure that you are looking at the index the right way, or you'll really F things up. So for insertion sort, we have a nested for loop. For an array X with n items, we go through each of those items, and we compare that item to the one before it. And if the one After a one before it is greater than it, then we swap it. Now notice that we are checking if it is less than the item before it in our for loop, not inside of it. This means that if we get to the point that our array is sorted before we've gone through every item, then the sorting is done. So it's fairly quick if you have an array that's nearly sorted, which is why insertion sort is good for that. So in this example, we have our reverse array, which is the worst case scenario for insertion sort. So first, I'm comparing item 2, comparing the number 2 to 3. Well, 2 is less than 3, so I swap them, and then I have x's 2, 3, and 1. And then I compare 1 and 3, and 1 is less than 3, so we swap them. 1 is less than 2, and then we swap them. And there we have our sorted array. And how many operations did this take? How many times did I do a thing? 3. And how many items do I have? 3. So in this situation, this is order of n, because the number of items equals the number of operations. Now insertion sort in the worst case scenario, because of that nested for loop, is n squared. But if the array is nearly sorted, or you have a small data set, like 3 items in the array, it's close to order n, which is why insertion sort is widely used, as opposed to bubble sort, which is also order of n squared. And a bonus for insertion sort is that it is a stable sort. All of the items that have equal values are relatively positioned. So Alex comes before Adam, and Juan comes before me in this situation. And it's really easy to implement in JavaScript from my pseudocode over to JS. Again, I have that outer for loop, the inner for loop that checks the items before it, and I just need a temporary space so I can swap the items in the array, and the function insertion sort takes in my array, and it outputs 1, 2, and 3, my sorted array. So that's just a few lines of code, and you have insertion sort. So now you have the option to do whatever the browser thinks it should do, usually merge sort. I think Internet Explorer uses a different one. Or if you want to use insertion sort, you can do that as well. And again, if you have a small amount of data and you don't have any space, insertion sort is great because it doesn't take much space. And for small data, it's really fast. Here is a cool visualization video of insertion sort happening. And if you go on YouTube and search sorting algorithm visualizations, you'll find some really cool, trippy stuff that you'll find yourself staring at for hours and hours, like I was doing yesterday. Very nice. Bubble sort, woo! Bubbles, yay! So bubble sort looks similar to insertion sort, and some people are like, well, what's the difference between insertion sort and bubble sort, and why does bubble sort suck and insertion sort doesn't? Well, in insertion sort, we are checking the values and how they compare inside of our for loop. But in bubble sort, we're doing it within the for loop. So even if the array is sorted, we still are checking through every item, which is what makes it slow. And in this example, we'll show you that normally you would just need 3 operations, but we still have to go through all those items as per bubble sort's algorithm, and so you end up not doing anything for 3 more operations, but you do end up with a sorted array. So it's at this point, the small data uses 2 times n, so you would just say order 2n or just order n. If you have a polynomial in your order, if it takes like n squared minus n operations, you drop all of the other values and just keep the highest polynomial. So n squared minus n, the order is n squared, which is really confusing, but when we're talking about really large amounts of data, anything smaller than that highest polynomial is just trivial. You guys hate me yet? So the implementation of bubble sort, again, is also really easy. And bubble sort is one of the first algorithms to be really studied, which is why it's still around. more for teaching theoretical, algorithm analysis. But again, we have our 2 for loops, which makes it pretty slow because we're going through every item twice. And then we have our if statement, and then we flip the items just like we do in insertion sort. And here in my example, I have a little bit of a larger array. It's a nested for loop again, so it's going to be a quadratic order for the worst case. It's not stable, and it's very easy to implement, but otherwise just whatever. Like, don't use it on things. It's really just like a learning tool. The greatest living computer science knowledge, Knuth in the Art of Programming, one of my other Bible besides the Corman Algorithms book, says that bubble sort seems to have nothing to recommend it except a catchy name and the fact that it leads to some interesting theoretical problems, which is a talk in itself. And if you want to read about those theoretical problems, unfortunately, you have to buy some computer science journals because, again, computer science professors like to keep everything behind a paywall. F those guys. And here we have bubble sort in action. So you see the red line? It's going through every item, regardless of whether it has to sort or not. So it's kind of like, okay, bubble sort, you can stop. And then it gets, boom, you're sorted. So it can be twice as slow as insertion sort, even if it has a smaller amount of data. So that's a good intro to simple sorting algorithms that don't involve cool, crazy things like recursion. Merge sort does require that, so it takes maybe 20 lines of code as opposed to 10 for implementing in JavaScript. So in our pseudocode, we are recursively doing this, so we're going to be taking our array and splitting it in 2, and then merge sorting those arrays, and then we break that array into smaller pieces until we have the smallest components of one item, and we compare the 2 single items and merge it, and then do the same and build it back up until we have our array that is sorted. So it's a logarithmic order. It's really fast. So in this example, I have an array 3, 2, 1, and I split it into 2. So then I have the array 3, which is itself, it's sorted, it's ready to merge. So then we just have the second array, 2 and 1, and we split that up into 2 arrays, 2 and 1. They're single on their own, ready to merge. So we merge it to 1 and 2, and then we merge it with 3, and then we have our array. There you go. It's a multi-branch recursion. We call this divide and conquer, because you're dividing and then just conquering the task. The order is n log n. Again, it's logarithmic because we're breaking up into smaller pieces, which is what you kind of want to look for in a sort, if you have the space and resources to do recursion. If you have a very, very large amount of data, you're not going to recursively sort it in the browser. The console will say, too many recursions, probably in all caps. Big data is not to be sorted in the browser. You need a large amount of memory and hardware in order to do that. So if you have to do a lot of data that has to be in the browser, you might look more towards insertion sort or selection sort as opposed to this one. It's fast and it's stable, which is probably why browsers use this. And here we have it JavaScripted. There's 2 parts, the dividing part. So we have a function merge sort. We split the array in half. So I have a left and then a right side array. And I merge the recursive call of merge sort on left and merge sort right. So not many lines of code for that. And then this is the sorted array merge function, which does a little bit more. It takes the 2 arrays that are their little pieces, usually 1 item, and it compares them and creates a merged array, sorted, and concatenates whatever pieces are left and right. And in the end, you have your really cool merged sorted array. This visualization comes from another YouTube account, so it's not using the same amount of data as insertion sort and bubble sort. If it was, this would be much faster, but this is so much more satisfying to watch, honestly. So at about 10 seconds, you see it's sorting those arrays there and merging the little pieces. And then watch this. Whoop, awesome. Let's get, and then these are close to almost being sorted. This is like the best part of sorting ever. Ta-da! Let's give a clap for merge sort. So here's your final exams cheat sheet for sorting. Remember, insertion sort, the worst case scenario, big O, is n squared, just like bubble sort, but it has low resources needed and it's fast for nearly sorted data. Again, it was O of n when we only had 3 items. It's slow when data is reverse ordered and large, so you might want to look for the logarithmic sorting if you have the resources. Bubble sort, just don't use it. It's slow as F. It's not stable. It's easy to implement and it has a cool name, Stalinus had said. And it's a good example to use when you're explaining sorting because it's always good to know what sorts are great and which ones are not so great and compare why. And then a lot of people come up with even better sorting algorithms adapted from multiple sorts together. And then you have merge sort, which is O of n log n. It's both fast and hella stable, but it needs resources for temporary space and arrays from recursive calls and can be memory intensive the more data that you have. So congratulations. You all now officially have a degree. Go out and teach algorithms. You can just go to a college and let them know I sent you. It's cool. But know that there are so many more other sorting algorithms out there that I can't fit into this talk. So go out and explore them and implement them and make your applications a little more optimized. Because again, that dot sort function might not be the best, case scenario for you to use in your data. Now you know that you can go out and fairly easily implement them in JavaScript or your language of choice. But you might be saying, you're forgetting the real important question that brought all of us here today, is that how can we use this to increase our SEO? The answer is yes. Thank you very much. If you have any questions, you can see me wherever later. I'll be around on a boat, I think.